Okay, this is a video following on from the one about reactance. This is a similar idea called impedance, symbol Z, whereas reactance was for single components. This is a property of an entire circuit. So just before we crack into that, let's go back over some AC phasor stuff that will be useful for what we're going to do here. If we've got a LCR circuit like this one, with an inductor, a capacitor, and a resistor, we can represent the voltages across it with phasors. We start with our resistor phasor drawn at the 3 o'clock position, just by convention, and it rotates anti-clockwise with an angular velocity of 2 pi times the frequency, the source power supply frequency. The capacitor voltage always lags the resistor voltage by pi over 2, 90 degrees, and the inductor voltage always leads by pi over 2, 90 degrees. I'm drawing this phasor diagram with the capacitor voltage being larger than the inductor, but it could be the other way around, just the principles are the same. If we wanted to find the supply voltage, we just add up those 3 voltages as vectors. So the supply voltage is the vector sum of those 3. So we would draw, for example, that doesn't matter what order you do them in, but we could do, if we went down the capacitor voltage, then across the resistor, and then up the inductor voltage, we would get the supply voltage would be from where we started to where we finished. If we wanted to find the size of the supply voltage, we could use Pythagoras. It goes across the resistor voltage, and it goes down Vc minus VL, the difference between the capacitor and inductor voltage. And we could use then Pythagoras to find the supply voltage. Also, just some definitions for resistance, remember, was the resistor voltage over current. Capacitor reactance is the capacitor voltage divided by current, or we could also find it by using 1 over omega c, omega being the 2 pi f for the source. Inductor reactance is also inductor voltage over current, and could also find inductor reactance by using omega L, and for all of those things, omega equals 2 pi f. So that's just a quick little summary of some ideas from some previous things that we're going to be using in this one. So let's talk about circuit impedance. I'm going to use the same circuit that I used for the reactance video with the same values. And from that video, I'm just going to put up here that we went through and we calculated in that video that the resistance we know is 2,700 ohms. We went through and calculated that the capacitor reactance is 2,950 ohms, and the inductor reactance was 1,390 ohms. If you want to see how they were done, go back and have a look at the previous video on reactance. Now, what to talk about now though is the circuit impedance. So impedance is the combined effect of all the resistance and reactance in the circuit. Okay, so we've got a resistor, a capacitor, and an inductor, and they have a combined effect that limits the current flow. We call that effect impedance. And its basic definition is exactly the same as the basic definition for resistance and reactance. It's just voltage over current. Okay, except in this case, because we're talking about the whole circuit, we need the whole voltage, the supply voltage. So it's the supply voltage divided by the current. Okay, so we divide the supply voltage by current, and that calculates the circuit impedance. And because it's a voltage divided by current, it's also measured in ohms. And again, those values, the voltage and current, could either be RMS or both RMS or both maximum values. It would give the same answer. We usually use RMS, like all these values are here are RMS values. So for this circuit, for example, if we wanted to calculate the impedance for this circuit, we just divide the voltage, which is 15 volts, divided by the, that's an RMS voltage, divided by the RMS current, 0.00482. Which gives us an impedance of 3,110 ohms. Okay. Now, that's assuming we knew the voltage and the current, but what if we didn't know those things? Can we determine it from the components in the circuit? Yes, we can. Okay, we can use the phasor diagram for it. Now, we started off with the we've done a couple of videos back about the phase relationships between resistors, capacitor, and inductor voltages and the supply voltage. Now, one thing about vectors, if I wanted to scale, if I wanted to change the size, let's say I wanted to, if I multiplied everything by 1.5, okay, I'd get all those vectors being 1.5 times bigger, but it would still all work, okay? Like that all still scale, that all scaled proportionally, so it would still work together. Or I could all divide everything by 2, and everything would be half the size and would still work. So you can multiply or divide a vector diagram as long as you multiply or divide everything in it by the same amount, okay? What if I took that vector diagram and now one thing to know is because they're all in series, they all have the same current. So what if I divided everything by the current? What's that going to do? I'm going to get a phasor diagram that's got VL over I, VR over I, VS over I, and VC over I. Now, if you're paying attention, you might recognize that those things are all the resistance, the reactance, and the impedance. So what I've actually got here is a phasor diagram that has got the inductor reactance, the capacitor reactance, the resistance, and the impedance of the circuit in it. So we can draw exactly the same phasor diagram as we had for voltage, but for the resistance, reactance, and impedance. Which means if we go back to that circuit, and we've already calculated what the impedance was using the Ohm's law version, but I can change this phasor diagram that we had in voltages. If we divide everything by current, we can turn that all into resistances and impedances, okay? And we can then use that to calculate what's going on in the circuit, okay? So if I just put in the values that we know that the resistor was 2,700 ohms, the inductor reactance was 1,390 ohms, and the capacitor reactance was 2,950. Again, if you want to know how we got those, the previous video on reactance has got those calculations in it. If we want to find the impedance of the circuit, Z, we just use Pythagoras, okay? Except that triangle on that there's got R along one side and the other side is the XC minus XL. It's the difference between the capacitor and reactor inductances. Capacitor and inductor reactances. So Z is the square root of R squared plus XC minus XL squared. And if we plug in the numbers that we have there, we find that we get 3,110 ohms. Again, it's the same value calculated in 2 different ways. Okay. Again, we could calculate that depending on what information we had. So if we had the resistors and resistor and reactances, we could calculate it using Pythagoras root, or if we had a voltage and a current, you could calculate it using Ohm's law. So let's go through an example for a calculation. Let's say we've got this circuit. Now this is different values than the one that we were just looking at. It's a 20 volt RMS power supply, 100 hertz, with a 1.2 kilo ohm resistor, a 1 microfarad capacitor, and a 0.85 Henry inductor. So what I want to know is what's the current in the circuit and what's the voltage across each component. And we'll go through how do we do this for this one. Now, first thing I'd calculate, it's not actually part of the question we had to calculate, but we're going to need it, is the angular velocity, the angular frequency, 2 pi f. So it's 2 pi times 100 hertz, which is 200 pi radians per second. I'm actually just going to leave it as 200 pi. I'm not actually going to bother multiplying it because it's just a calculation step. We're not. We're going to use that number for other things. So we'll avoid rounding errors if we just leave it as 200 pi for now. So first of all, I want to calculate. Well, we don't need to calculate resistance because we know what it is. Okay. So I'm going to start putting these into a phasor diagram. Now the resistance phasor is at 3 o'clock. And we know it's 1,200 ohms. Okay, we now need to know, we're going to go through each component, the capacitor reactance, 1 over omega c. So that's going to be 1 over 200 pi, that's omega, multiplied by 1 times 10 to the negative 6, that's the capacitance, which gives us a capacitor reactance of 1,590 ohms. Okay? And remember that capacitor reactance always lags resistance by pi over 2, so that's going to be straight downwards. Okay, so the capacitor reactance is 1,590 ohms downwards. The inductor is omega L, so it's 200 pi times the inductance 0.85 is 530 ohms. And remember that the inductor reactance leads R by pi over 2, so it's just going to go up 530. So if I want to find the impedance of the circuit, I have to add those together, okay, but as vectors. So if we go down the XC, across the R, and then come back up the XL, we get this vector for Z, where that side is the difference between XC and XL. So we use Pythagoras with R squared plus XC minus XL squared and plug in the numbers that we've just calculated. We get an impedance for the circuit of 1,600 ohms. Now we can use that now. We know the impedance of the circuit and we know the supply voltage. We can find the current by using Ohm's law, Vs divided by Z. So it's 20 volts divided by 1,600 ohms. This gives us a current of 0.0125 amps. So that's the current in the circuit. So that's one of the things that we were asked to find. Now we need to find the voltages across each component. And we can do this just by using Ohm's law for each component. We've got the current and we know the resistance or reactance for each component. So we can just use, for the resistor, V equals IR, which is 0.0125 times 1200 is 15.0 volts. And then we just do the same thing for each other component. For the capacitor, it's the current times the capacitor reactance, 1590, which gives us 19.9 volts. And the same thing for the inductor, which is the current times 530, which is 6.6 volts. Okay, so we can calculate all of those things, knowing how to calculate each individual reactance and how they relate in a phasor diagram. So, a quick summary of all this. The impedance is the combined effect of all the resistance and reactance in a circuit, which is defined basically by a slightly different version of Ohm's law. Z is the supply voltage divided by current. Resistance is the opposition to current flow because of the material, which is R is VR over I. Capacitor reactance is opposition because of buildup of charge on the plates of the capacitor, which is also voltage over current, but we can also find it using 1 over omega C. Inductor reactance is opposition because of induced back EMF, which is again voltage over current, but we can also find it using omega L. And we can relate all those together in a phasor diagram to find the impedance of a circuit using Pythagoras. And just useful to know, because we use it a lot in here, omega is 2 pi f. Okay, hope that helped.